will start that by really briefly explaining that one of the key areas in performance and parallel fuzzing is that most fuzzers out in the market are actually software-based tools, and they are very easy to speed up, or if you need, you can actually make them quite mobile as well. So depending whether you test an individual device or whether you test a complex network, you can use software-based solutions in lots of different environments. You can virtualize everything. You can use even clusters of computers in generating those test cases. And it's really up to your design of your test environment, which setup is best for you. If you need any help, of course, our personnel are always available for you, but understanding the scale of fuzzing is really, it depends on your own test requirements. So even though the topic here is performance and parallel execution, that's not necessarily what you want to do in your specific tests. And there's many reasons for that. One reason why you might want to do fuzzing is the aspect of anomaly coverage. So if you want to scale up all the anomalies and try to generate more test cases, if you end up having millions and millions of test cases for every single protocol, then of course time is critical in the test execution. On the other hand, if you have optimized your fuzz tests so that you only have like 1,000 test cases, then you don't necessarily need to speed up the test execution, especially in the early steps of the product lifecycle, or if you have to test a lot of complex different protocols, then speed actually can create problems for the analysis of the test results. So you have to be very careful how you choose to do your high performance fuzzing. But using software-based tools, it's very easy to actually measure and optimize your test execution in order to create load. And with that, I don't mean load in traditional load testing or performance testing perspective, but create load in the fuzzing process. So if you go to our website and look under solutions performance testing, you can see more details on our study. But in short, we tried a lot of different protocols and we saw different bottlenecks in different test setups. And also we analyzed different impacts from different configuration items in protocols and in the tools, and how those impact the actual test execution. But as a summary anyways, protocols, if we look at some of the results that we have here, DNS running with the capture tool reads really significant numbers, like tens of thousands of test cases per second, and whereas more other application level protocols like HTTP had like 1/3 of the performance of the capture tool. Immediately you can start analyzing some aspects, some attributes to these results. So of course, if you look at HTTP, it's a simple request response protocol over TCP, whereas DNS is a UDP protocol. So the handshake process inside TLS, inside TCP can of course impact the speed of test cases. TLS on the other hand consists of high complex cryptographic algorithms that need to be modeled, and then each one of those test cases consists of a complex message sequence, and therefore, of course, the test execution is much slower than simple request response protocols. With protocols like IP version 6 or IP version 4 or routing protocols, the REST restrictions often come also from the protocol stacks themselves that are used. For example, in IP version 6, we are modeling the entire IP version 6 stack in order to be able to test every single variant of those packets. So it can be slightly slower than running, for example, HTTP over IP version 6, which is, of course, should be about the same rate as these tests done over IP version 4. But anyways, you need to look at those metrics on your own setup, and the purpose of this presentation is just to give you ideas how you can speed up your test execution. Some reasons why we actually started looking at this topic, in addition to requests from our customers, we were also interested in just measuring how fast test cases, test generation we can reach with our current tools. Our tools are not aimed for performance and they are not optimized for performance. We just measured how well they can actually do in high load situations just as they are without any speed optimization. And then look at the actual benefits of using the same model-based test generation tools even for conformance and performance testing, because all of our tools come with a wide range of different valid conformance tests, conformance-like tests, although the focus is really in the security testing and in the fuzzing aspect of it. And interestingly, already we've seen lots of our customers looking at even comparing the price benefit and the feature benefit against traditionally appliance-based performance testing tools. Of course, those devices always often reach higher data rates because they have very low-end hardware optimized for speed. But on the other hand, model-based fuzzing tools provide capability to build your own test scenarios, edit those models, and combining that with high performance actually might make them interesting even for traditional performance testing areas. So looking at metrics in fuzzing performance and parallel fuzzing, we were initially looking at traditional load metrics from performance testing as well, but we noticed that quite often people were talking about packets or bytes per second or protocol transactions per second. There's lots of different terms used for load and performance scenarios, and none of those really seem to match in fuzzing. So what we ended up using in the white paper and in the materials you can download from our website is just staying with the actual concept of test cases and looking at how many test cases each one of those protocols can do. So if you look at the metrics of looking at how many different test cases per second each one of these execution threads or test generators can create per second or per minute, and then look at how many parallel test generators you can actually have running, then the combination of those gives you the test cases per second, or we often use TC/S test cases per second for that. And if you look at a chart like this and try to match that into traditional performance testing, the biggest difference is that we try to go through a complex protocol sequence as fast as possible. So we are not really simulating real users. So if you compare this to web testing, where you are simulating 10,000 parallel users, you are actually adding a lot of delays in between those message exchanges. Same in voice over IP, you wouldn't do this really tight loop inside each test case in order to push more test cases through, which is critical in fuzzing.